Hello.
Hey!
Hello, Mr. Aaron. Ryan. That's it. How are you today? It's Friday. Good?
Hello!
Okay, that's it. Okay, so today we'll talk about binary tree again. So what's binary tree, Eric?
A tree.
A tree. What binary means?
Two.
And what's binary tree? Can you draw an example on the board, please? Just any example, yeah.
Here, how are you draw it?
Yeah. Any example, yes. Any binary tree. Any, just any binary tree. Oh, that's a nice drawing. You don't need to draw that perfectly. Wow, that's good.
Like a shooting star.
Yeah, well done. Yeah.
Yeah. I'm gonna do 1.
Okay. Pick any numbers.
2, 3, 4, 5.
Okay, that's very good. Any numbers will do, please.
Okay, so I'll choose 8.
Okay.
I love to eat burgers.
Okay, well done. So what in this particular binary tree? What are the leaves?
2 and 8.
2 and 8. Why is the leaf?
Because it doesn't have any pets, children.
And what's the root? How many roots does the binary tree have? What does the root? What's the root?
1.
1. And how many binary tree?
It doesn't have a parent.
Okay, it doesn't have a parent. So only one root in the binary tree. Okay? Yes, does it make sense?
Yeah.
Okay, so now look, if we see the numbers from the root to the leaf. So what's this? If you get the numbers continuously from the root to the
12.
it's not no. I'm saying that 192. Okay. 192.
192.
And then this
18.
18 plus 18. So you got 210, right?
Yeah.
Okay, so this is the task for today. So we first of all we get list the numbers from the root to the leaf, and then we sum it together. Okay, does it make sense? Yeah. So any idea how we can do it? How many ways of traversing the binary tree? How many ways of traversing?
Breakfast search, depth search.
Breadth search and depth search. So what's the difference between breadth search and depth search?
Sometimes they are the same,
Yeah, but what's breadth search?
level by level.
So in this particular set,
Is 1982.
1982, okay? 1982. And what's the depth search in this case?
1928.
1928. So it's the same, yeah? Yeah?
It's
Oh, it's not the same. Okay, and how about, can you list the example that the breadth search and depth search is the same? Can you draw a tree, or can you think of example that you just remove these two, and then the breadth search that will be 192, right? 198, right? And the depth search will be 198, right? As well, yeah? So you erase 2, right? Does it make sense? Yeah? So that's the case when breadth search and depth search is the same. Or the single node. Yeah? If the single node, the depth search and breadth search is the same, right? Does it make sense? So today we're going to use the breadth search to solve this problem, and tomorrow we're going to use the depth search to solve this problem. Is that okay? Yeah. Okay, so in order to breadth search, what kind of data structure are we using to implement the breadth search, please?
breakfast search.
No, a breadth search, what kind of data structure can we use? Data structure, I'm talking about...
Queue.
Queue, yeah. And what's queue?
First in, first out.
First in, first out. Yeah.
Yeah.
Yeah, first in, first out. So first in, first out, for example, like 1, 2, let's do this, and 3, and that's 4 here, right? Okay, so at the beginning, the queue is empty, and the first node we need to put in the queue is which node?
Root.
Root, which is what?
Which is 1.
1, okay. Then we take this one out. Every time when the queue is not empty, we take it out.
Yeah.
And what do we do next? We take it one out. The queue. We call it the queue. And what do we do next? What do we do next? We take the kid out and we push
Push it in.
Push
Pop
it.
it.
we pop it, which is the queue, and we push the kids
Yeah. Which is 2 and 3.
2 and 3 into the
Q.
yeah. So I take it out.
Yeah.
I put a 2 and 3. Okay, so next time I take what out? What numbers out? Next time I take which number? 2 or 3 out?
You take out 2.
2, yeah, the beginning of the queue, yeah? Because the DQ is the beginning of queue, like you were waiting in the queue, yeah? You're buying something in the queue. The beginning of the queue gets served next, right? And when the people come in, join the queue, they join at the back of the queue, alright? Does it make sense? Oh, we take a 2 out, and what happened? If I take a 2 out, what should I do next? I take a 2 out, and what do I do?
You shall
Is what? What?
rub out 3.
No. I take the 2 out. What's next? I need to.
4 at the end of 3.
Yeah, I take
And
it.
take both of them out.
And then 3, take it out, but it doesn't have a kid. Then what should we do? If it doesn't have a kid, then I need to sum this value 13. Yeah, I need to note down the value 13. Yeah.
Yeah.
And then take the 4 out, which is the
14. No, 134.
yeah 124. That's it. So look, this is the basic procedure of buffer search, but we also need to remember the current value from the root to the leaf to the current node, right? Then how can we do it? If it's 1, look Eric, look, it's 1. I want to make it. Eric, come on.
Yeah.
If current node is 1 and then we have if the root node is 1 and then we know the next node is 2, so how can we make 12? So I have 1, I have 2, how can we make 12?
You just
What?
write them up. 1 and 2.
Yeah, but 1, how do 1 and 2 make 1, 2? Mathematically, not string, mathematically.
You put it together.
No, and how do we put it together? Like what 12 and 4, how do we make 124? Putting it together mathematically, there's no operation.
Times 10 and add 4.
Yeah, that's what I'm asking. 1 times 10 plus 2. Yeah, so every time you want to push it to kid, you need to times current value by 10 and add the new value. Alright? Does it make sense?
Yeah.
Okay, let's do this, okay? Breakfast search. Does it make you hungry, breakfast search? Yeah. Breakfast search, not breakfast, okay? Breakfast search. And we call it root, the root of the tree. What's missing?
Color.
If root, first of all, we have to check if the root is empty or not, right? If root is none, we should return what? If it's an empty tree, what's the sum of the empty tree?
0.
Yeah, well done. And then in Python, what we are implementing a queue, so queue equals what? What kind of the
DQ.
DQ? Yeah, what's DE mean?
Double-ended Q.
Well done. And then I need to add what we should know is it?
Wait.
Root. This is a set and I need to add a tuple, yeah? Root and the root of value, yeah? Because I need to remember the value of the current node from the root to the current node. This means the integer from the root to current node, okay? Okay, then while what? We need to check if the queue is not empty. How do we check if the queue is empty or not? While what?
While Q is
What?
not 0.
Not 0, bigger than 0. But Q, how do we check the size?
Column.
How do we check the size of Q? There's something missing here.
Length.
Length, yes, well done. And then we need to get the Q. And how do we dequeue it? How do we get the element from the Q? Pop it.
Yeah.
Pop left or pop?
Pop left.
Okay, now we need to assign it to current and then value, yeah? Value. So because each element in the queue has 2 elements, right? Each element in the queue is a tuple with two values, right? One is the node, one is the value. So look, it's q dot pop left, right? Right? Alright. Okay, now we have the current and we have the value. And how do we check if a node is a leaf node?
And It doesn't have any.
It doesn't have any what?
Children.
Children. And how do we check if it doesn't have a children? If current dot left is what? Is what? If it doesn't have a children, what should we do? If current left is what?
Is
The magic word is what? Doesn't have it. So what's the?
please length.
Is what? None. Come on, none.
Oh,
Yeah. Here, look, none. And look, this is n. Yeah. Current dot right is what?
And current dot right is none.
And what's missing?
Column.
Well done. If it's a need to know, okay, then let's add this answer in the answer, yeah. So what should we do now? If it's a leaf node, what should we do now? All right. If it's a leaf node, what should we do?
If it's a leaf node, we shall add it.
Add it to what?
Answer.
Answer. Add it equal what?
Value.
Very well done. Okay, then if current if it has a left node, what should we do? All right. If the node has a left node, left kid, all right, what should we do? If the node has a left node, what should we do?
We push it in.
Q dot up what? Q dot what?
First you
A
put
pen.
Append. Yes, Ryan, good job. Append what? Append what?
a pen.
Left.
Current dot left. Yeah.
Current.
And what? And then value. What's the value?
Times 1.
This is the value. Value. And then this is the previous value. And then this
Times
is
10
add what?
Current value.
Current dot left value because we're talking about the left. Okay. And if current dot right, what? If current dot right, what should we do?
in current dot right. Q dot append the current dot right. Value times 10 add current right. Wait. Dot right.
What? Dot.
Dot value.
And what's missing here? Well, there's something missing in the code. So what should we do now?
Return.
Return. Yeah, return what?
Answer. No.
Well done. Yeah, return answer. Come on, you are paying attention. Yeah, good job.
Not
Good job.
ask.
Yeah, well done. Oh, you're just guessing. Huh?
I'm not guessing.
Okay, well done. You're paying attention. Very good. Good job as well. Okay, for answering this, it's very good job. What's the time complexity?
Or
Definitely
Oh,
something.
something. Yeah. If there are n nodes in the binary tree.
N.
Yeah, well done. Because we're visiting each node exactly how many times?
N times.
We are
One.
visiting it, yeah, one time. Okay, what's the space complexity?
O-N.
Why so n?
Because we're using
a
a
binary
DQ.
tree.
Yeah, DQ, yeah, because we're using an additional space to keep the nodes
Yeah.
in the, yeah, we are in queuing. In queue means push something into the queue. DQing means take something out of the queue, okay? In and did is the different operations, okay? That's very good, that's very good. Okay, so that's it for today. Say bye-bye to people. Say bye-bye to people and see you tomorrow. Oh. Bye-bye. Good job, good job.